Ladies and gentlemen, very good morning and warm welcome to Asia CCUS Network CCUS Technical Workshop, organized by ERIA with the support by Mitsubishi Research Institute, Japan. I am Dian Lutfiana, Research Associate of ERIA and Asia CCUS Network, and I will be your MC for today's workshop. We are coming to the day 3, last day of CCUS Technical Workshop. Today, we will hear lectures about carbon utilization from Pertamina Research and Technology Center Indonesia and National University of Singapore. Before continuing the main agenda, I would like to briefly explain about housekeeping rules. We will have Q&A session after each presentation. Participants can drop your questions on Q&A box during the presentation. Without further ado, it is my pleasure to invite Dr. Han Phoumin, Senior Energy Economist of ERIA, to deliver his opening remarks. Dr. Phoumin, the floor is yours.
Thank you very much, Dean. A very good morning, supporting member of Asia CCUS Network, and also distinguished participants, ladies and gentlemen. Once again, warmly welcome to the third day of the series of technical workshop on CCUS. Today, I'm very pleased to make a brief opening remark for the third technical workshop on the aspect of carbon utilization technologies. The 3-day continuous technical workshop share all the needed aspects that policymakers may need to know in order to get themselves familiarized with the technical understanding on CCUS, particularly on the carbon capture technologies, which were discussed on day 1 of the workshop, and carbon transportation and storage, which were discussed yesterday on day 2. And now it's coming to the 3rd day that we will discuss on the carbon utilization. One way to reduce emission is the carbon recycling. After the CO2 is captured, the CO2 is used to create new material and products. Instead of just sequestering the CO2 will be utilized to make everything from fuel, concrete, and so to cleaning products, plastic, and food. This allows us to actually recycle the emission and create a circular carbon economy. I just want to reiterate that why this technical workshop is so critical and timely important for Asia, because Asia will need to redesign the policy in order to ensure that carbon sink technologies such as CCUS can be deployed in Asia context to deal with emission as we are looking forward to the carbon neutrality by the mid-21st century. In this regard, Asia CCUS Network mission is so critical as its mission is meant to promote knowledge sharing through holding annual forum, conference, workshop, and meeting, and also conduct research study on various kinds on technical, economic, and legal aspects of CCUS in our region. And lastly, we also continue to hold capacity building training workshop to break the knowledge gap on CCUS. We as the Asia CCUS Network Secretariat will continue to organize such technical workshop as part of the capacity building training to bridge the knowledge gap on CCUS. We believe that in supporting the development of CCUS policy, technical experts in Asia will need to understand the technical aspect of CCUS. And we hope that today's technical workshop will enhance the technical understanding on these CCUS technologies. Let me take this opportunity to thank MOI in particular for their working hard with Asia CCUS Network to host a series of technical workshops on CCUS. Particularly, I want to thank Ms Kikuko Shinchi and her team from MOI for their support and collaboration to make this workshop happen. Also, on behalf of the Secretariat of Asia CCUS Network, I also very thankful for today's speaker, particularly Mrs. Dewi Mersitarini, the advisor on CCUS Pertamina, Indonesia, and also Professor Ning, the Dean Chair Associate Professor, Head of Green Catalysis Lab, National University of Singapore, that going to dive into that lecturing for today. Last not least, please visit our website, Asia CCUS website from time to time for our update on activity. I would like to stop here, and I hope that you will find today's technical workshop very useful. Thank you very much. Back to you, Dian. Thank you.
Thank you, Dr. Phoumin, for your opening speech. Continue to the next agenda. Ms Kikuko Shinchi, Senior Researcher of Mitsubishi Research Institute, will give her introduction remarks. Mrs. Shinchi, the floor is yours.
Thank you, Ms. Dia, for your kind introduction. My name is Kikuko Shinchi. I'm a Senior Researcher at Climate Change Solutions Group of Mitsubishi Research Institute. I would like to extend a warm welcome to all the participants and speakers, as well as gratitude to ERIA for entrusting Mitsubishi Research Institute, or MRI, to organize this technical workshop. I would like to take this time to give a brief overview of the technical workshop series and some underlying information regarding CO2 utilization, which is the topic of today's discussion. The technical workshop was proposed at the first Asia CCUS Network Forum held in June this year. Professor Nishimura, the president of ERIA, said in his keynote speech that knowledge share and capacity building training workshops are crucial to bridge the knowledge gap on CCUS. Building upon the outcome of the first Asia CCUS Network Forum, we have organized this virtual technical workshop. The goal of the workshop consists of three main topics. One, promote the knowledge sharing on the latest CCUS technology through the lecture sessions. Two, accelerate further consideration of application of mainstream CCUS technologies to the ASEAN region. And three, exchange ideas and issues about CCUS technology. I hope the participants today take back the information gained through the lectures to your country or organization and consider them in implementing your CCUS strategy. As mentioned already by Dr. Han Phoumin, we have separated the workshop into three sessions. On day one, we covered carbon capture technology. Day two, we focused on transport and storage technologies. And day three, the final day, which is today, we will discuss technologies for utilization of CO2. I'm going to briefly describe what we covered in day one and day two for those participants who may not have participated in these 2 days. And if you're interested, you can access the online recording later on from the ERIA website. Day one session featured lectured by two experts. First, Dr. David Kearns from Global CCS Institute. He shared with us the overview of capture technologies, their characteristics, including cost and carbon footprint, and other points to consider, such as the gas characteristics, available energy source, and space, when deciding which technology is suited for each application type, and suitable underlying conditions for application. We also welcomed second lecturer, Mr. Takashi Kamijo, Chief Engineering Manager, Project Director of Decarbonization Business Department of Mitsubishi Heavy Industries Engineering. Mitsubishi Heavy Industries Engineering is the world's leading technology provider in carbon capture and has a decade-long track record of installing carbon capture plants around the world, including the Southeast Asia region. He shared with us not only the technical information, but also on the actual application cases to various industry sectors. On day two, we covered the topic of carbon transportation and storage technologies. I was very pleased that we had two speakers lined up to share with us their expertise and their research findings. Mr. Ulysses Comas, my colleague at MRI, has been researching CCUS business models around the world. And through his experience engaging with project developers around the world, he shared with us his findings on transportation technologies that are found in some of the most prominent projects of CCUS. And discussion following his presentation revealed that there are still issues that remain in effective using of existing infrastructure, such as pipeline, as well as utilizing new technologies such as shipping and other methods, in particular to the Southeast Asian region, where many countries lack the existing infrastructure. Dr. Ziqiu Xue of the Research Institute of Innovative Technology for the Earth, or RITE, is a very experienced researcher in the field of CO2 storage. And he shared with us his institute's research outcomes in the behavior of underground CO2 and points to consider for permanent sequestration of CO2, including its monitoring. And we have finally come to day 3, the final day. And as mentioned already by Dr. Han Phoumin, we have 2 distinguished speakers to share with us their knowledge on carbon utilization technology. Ms. Dewi Mersitarini of Pertamina Indonesia and Professor Ning of National University of Singapore. They will share their leading R&D activities while also touching upon industrial application possibilities. I'm very excited to welcome these speakers to learn about business opportunities in industrial development possibilities. And before I will ask our lecturers to come forward, I would also like to share some background information on CO2 utilization situation in Southeast Asia region. IEA's research has estimated that currently approximately 230 megatons of CO2 is used, mainly by the fertilizer industry for production of urea and oil and gas industry for enhanced oil recovery. The remaining small portion is used in beverage, cooling, and water treatment sectors. At the same time, IEA scenario indicates that future needs to look different. In the IEA Sustainable Development Scenario, which looks towards 2070 for carbon neutrality, of the CO2 that is used, around 95% is used as feedstock for synthetic fuel production, the main user being the aviation sector, while the remainder is used in the chemical sector. This represents a major change in how CO2 is used. As mentioned earlier, today, the majority of CO2 is used for EOR, where nearly all the CO2 is permanently stored, or in the chemical sector, where the CO2 is captured and used in the same process to produce fertilizer, and which gets ultimately released into the atmosphere. In the immediate period up to 2030, CO2 used for synthetic fuel production is expected to scale up gradually. The shift towards 2070 increases CO2 use by around 3/4 relatively to today, starting from a small base, and paves the way for greater deployment for synthetic fuel in aviation sector in the long term. As for the source of CO2, the IEA Sustainable Development Scenario estimates that all synthetic fuel production uses CO2 sourced from direct air capture directly from the atmosphere or from biomass by 2017. However, in the more immediate terms, the CO2 will continue to come from industrial and fossil fuel sources. So this shift of CO2 source from fossil to industry to biomass or DAC is very important in realizing a carbon neutral future. Unfortunately, CO2U is not an automatic answer to decarbonization. As mentioned briefly already, for example, when CO2 is used for fertilizer production, it will eventually result in CO2 release into the atmosphere. And in order for CO2 utilization to contribute to climate change mitigation, LCA or life cycle assessment of CO2 reduction is a key. And for that, there are several points to be considered. One the product or service the CO2-based product or service is displacing. Naturally, if the CO2 utilizing product can displace fossil-based product, it will have an impact on CO2 reduction. And two, how long the carbon is retained in the product. As mentioned already in the example of using CO2 to produce fertilizer, where CO2 is eventually released into atmosphere upon utilization. So we want to make sure that retainment or permanence of CO2 is secured for climate change mitigation purpose. The long-term sequestration becomes a very important issue. Three, the source of CO2, whether it comes from fossil fuels, industrial process, or biomass, or the air. As mentioned already, it is naturally that CO2 reduction impact is greater if CO2 itself is sourced from biomass, which is considered carbon neutral, or the air itself, as opposed to fossil sources or carbon-intensive industrial process. The fourth point is how much and what form of energy is used to convert the CO2. Again, this may be obvious to many of you, but when considering the life cycle assessment reduction of CO2, the form of energy is quite important, especially when many methods of CO2 conversion process may require substantial energy use. To have a high life cycle assessment impact, we need to have energy that's sourced from renewable sources. And last but not least, the scalability. And from both the economic perspective and the CO2 reduction impact perspective, we would ideally like the technology to be scalable in size and also replicable so it can be deployed in many areas. It is interesting to note that Elon Musk, the founder of Tesla, is running a $100 million X Prize contest for carbon removal technology right now. And the conditions for this prize include the life cycle assessment, permanent sequestration of CO2, and scalability. With this, I would like to conclude my introductory remark and hand over to Ms. Diane again. Thank you very much.
Thank you, Ms. Shinchi, for your introduction and brief explanation on consideration using CO2 as part of climate change mitigation efforts. In proceeding to the next session, we will have a presentation on research activities of CCU technologies in Indonesia by Ms. Dewi Mersitarini, Advisor CCUS Pertamina Research and Technology Center, Indonesia. Ms. Mersitarini, the floor is yours.
Thank you, Diane. Okay, good morning, selamat pagi, ohayo gozaimasu. Nice to meet you all. In our today's event, CCUS Technical Workshop as part of Asia CCUS Network Series program. It's been an honor and pleasure for me to be here, and a big appreciation to ERIA committee members and also MRI for inviting me and giving me the opportunity to share with you all our progress in delivering CCUS plan and implementation. I'm Dewi Mersitarini, lead of CCUS Research Technology Innovation, PT Pertamina Persero. Next, please. As commitment to ESG, environmental social governance, Pertamina developed strategy to ensure environmental sustainability by addressing climate change through several decarbonization programs with target of reducing carbon footprint, as well as social sectors and also governance area. Next, please. CCUS implementation is a key to sustain energy supply with current business model by enabling to store carbon dioxide into subsurface formation, which may give benefit to enhance hydrocarbon production, also involving CO2 recycling that convert CO2 into value-added product, or we call it a CO2-based product. In here, we do the resource identification of the CO2 in our field area, and then we have several CO2 capture that develop in the upstream. Currently, it used for the gas treatment process to fulfill the gas sales composition requirement. And then we do some of the CO2 to our buyer as a CO2 off-taker, delivering through pipeline. And then we do also currently the study for the CO2 injection and also the utilization of CO2 into several products. Next, please. So CO2 utilization is promoting carbon circular economy. So by reducing the carbon footprint, we remove into a safe containment in the subsurface formation, and then integrate with the renewable energy source, such as hydrogen source coming from the renewable geothermal power generation, and then recycle or reuse the CO2 into methanol product to be blended with the gasoline, also to produce the MA product to substitute the LPG. And moreover, it will reduce the portion of the fossil fuel. Okay, next, please. So we are doing two different approach. First, by engage with the technology provider to exercise any technology available and applicable by now, which might be ready to be implemented. But as in my experience, even some of them are still in a pilot stage. But we actively develop our library by mapping any resources available in our field, such as the CO2 source, potential hydrogen source, and the excess of hydrogen coming from hydrogen plant or in the off gas, and then potential utilities that can be used in any field area, and then potential excess capacity of renewable power generation. And the other approach is our research and development that we develop in-house. As you may have seen, currently we have a research for developing CO2 into precipitated calcium carbonate, and then microalga cultivation, CO2 to methanol via direct electrolysis, and then CO2 to DMA by CO2 reforming of methane, and then also catalyst development for polyurethane CO2 based. Okay. So here are the current study for the CO2 injection into two subsurface area in Gundi and Sukawati field. In here, we expect to reduce the carbon dioxide by 18 million in total. And hopefully the study soon we plan to proceed as we expect the study to be done by early next year. Okay, next. So CO2 is a stable molecule and having a low energy. Some application of CO2, as you may see in here, several products can be obtained by utilizing the CO2. And by converting CO2 into a valuable product, it's not just a way to reduce carbon emission, but moreover, it will bring economic value, growth to economy by generating revenue from new portfolio product, absorb more human resources in the employment of the industry, and also local resources utilization in your specific area. But it may not probably permanently taken away the carbon emission from the atmosphere, but this effort will make the chain longer of the CO2 usage before it really emitted to the atmosphere. And once finally the CO2 being emitted, we expect the natural sink and also the maturity of technology direct air capture might be already available during the time. Okay, next please. So here are one of the example of the utilization of the CO2. Pertamina is not doing this, but we selling the CO2 into the CO2 buyer or CO2 off-taker, and the CO2 buyer delivering the CO2 into several industries such as the carbonate drinks and also the dry ice production for the cooling agent. Next, please. And here are the CO2 mineralization. So the metal oxide and the CO2 using the current research that we have will develop into the metal carbonate, can be magnesium or calcium. In our case, we use the calcium oxide available in several areas in Indonesia, Sumatra area, and also Java area. And we get a calcium carbonate precipitated, which will be used for the filling agent in the paper industry, paint industry, tire industry, pharmacy, cosmetic, food industry, and others. Next, please. And we proudly present that we currently already develop the precipitated calcium carbonate in our in-house. So starting from the basic research, and then we already have the pilot plant 2 kilo per hour. And next, it will be field testing in our Subang field area. Subang field is a gas pull station from our upstream, which delivering the gas into our gas buyer. And we plan to develop the demo plan for the 20 kilo per hour in the 2022 and 2024. In this research, we got a grant fund from KMNQ. So hopefully it shows the triple helix is applied in here between the industry, university, and also the government. And you may see that we got two different structure of crystal, calcite structure, and also aragonite structure, and having a high purity, more than 99%, CO2 conversion up to 70%. And we're using natrium chloride as a solvent, and also it's having a high grade of PCC, which already start to be trial in the industry. Okay, next, please. And for the methanol, as we also having a study to develop the CO2 into methanol. Methanol is a high energy density. It's a quite stable solution, so it's easy to be stored, and it can be used as a fuel directly, or it can be used as a gasoline blending together with the alcohol, and also in the application of direct methanol fuel cell. So you may see methanol is also can be used as a feedstock for the next industry development, product development. Such as a polymers and then other product. Okay, next, please. And here are the application of CO2 to methanol in our research. We're integrate the research with the energy coming from the solar PV, as you may see there, and we're using the Catalysis copper zinc oxide on the cathode side, and then on the anode side we're using platina carbon, and the reaction is an atmospheric reaction. and we call it a membrane electrode assembly. So there is a cathode and then membrane electrolyte and then anode that being assembled together. And you've seen there when the water come into the anode, and then it will break the chain in the layer of the catalyst, and then the hydrogen will be crossing and migrate into the other side and doing the reduction with the CO2, and it will produce the methanol. So the CO2 on the other side is coming in on the cathode layer and being reacted with the hydrogen, hydrogen plus that coming from the other side. And then you can see we get the product in the of CO2 in percentage above 30%. And some of the unreacted CO2 will be separated. Okay, thank you. So in here, we also got a really appreciate that we got a funding from the government for the next stage of scale up of this research into the next stage. Okay, next please. And here are some of the CO2 capture and will be utilized into methanol that we currently do some study and also development in our field, in geothermal field and also in upstream field. We expect to get a green methanol by capturing CO2 source from the non-condensable gas. And we will be synthesized with the hydrogen coming from the electrolysis using the renewable electricity, renewable energy from the geothermal area. Currently, the status is we already have the hydrogen plant pilot for the green for the electrolysis. And next, we will continue to evaluate and synthesize it with CO2. And for the upstream field, we plan to have a blue methanol. Currently, we evaluate the field having a high CO2 content together with the methane as a feedstock with the low capacity of steam, synthesized into syngas and then syngas into methanol. We do both in this research by reviewing the current technology available, applicable, and also develop our in-house research. Okay, next, please. Okay, here are a natural gas with the high CO2 utilization. From here, I'm trying to show you that how the steam reforming work. If using only the methane, it will give you a syngas with the high hydrogen per CO ratio. So you may get 3:1 if you use a methane and using the steam reforming. But as we currently having a study to use as much as possible the CO2, so we start to have the CO2 reforming with less of steam. So you can see on the arrow more to the right, so we got the lower hydrogen per CO ratio. But you may also having a different product, yeah, by having that different ratio of hydrogen per CO. So in this case, as we aim to get a DMA, so we aim to get the hydrogen per CO ratio around 1 to 1.5. Okay, next, please. So here are our project catalyst development for the CO2 reforming, which currently already in the stage of producing syngas of CO2 and methane reforming without introduction of steam. And we got the hydrogen per CO ratio on 0.78 by now. And we will introduce steam to be able to reach at least 1. So, and then after that, we continue the reaction into the direct DMA. So we call it direct DMA because from the syngas is not following the methanol path before get into DMA, but directly from the syngas into the DMA. And you mentioned there the catalyst is currently using the cobalt, ruthenium, zirconium, silica in a pellet or flex crystal shape around 1 micrometers. And hopefully soon we will be able to continue this development into the DMA production. And the DMA will be currently planned to use for the LPG substitution and also will be used for other usage. Okay, next please. And here are another research in our site on the study of CO2-based polyol for polyurethane synthesis. Currently, it is in the stage of catalyst development. You mentioned the usage of the polyurethane for the coating, adhesive sealant, and elastomer, and so on. Okay, next please. And here are the crystal of the catalyst using the cerium oxide with the metal doping. Okay, next please. And next is the biocapture, or we call it natural sink, because it's the most actually the natural way to reduce the emission is using the path of reaction of photosynthesis. So you've seen that many kind of plant has been introduced and used as we have the removal rate of the forest, mangrove, and also alga. Alga is the one that microorganism that can be manipulated. So we expect that by having this, we could absorb CO2 as much as possible, and then we may still gain a good quality of product from the extraction. Okay, next please. So here are our research together again with the collaboration with the university. So we're using several strain of algae, chlorella, and then spirulina, and then nanochloropsis in doing this biocapture. And from the biomass, we do the extraction into the antioxidant, the pigment, and we use it for the food grade and also the feed grade. And you've seen we're using two methods in here, direct injection and also carbon trapping. So we're using the natrium hydroxide, and then we have the CO2 flow to trap the CO2, and then we got a natrium bicarbonate will be used as a nutrient for the microalgae, and then from that we do by doing those two, direct injection and also carbon trapping, we gonna have an option on how we gonna flow the CO2 into that solution. It might be which might be easier and which might be more applicable, because every strain is every single individual having its own characteristics. So we need to define and we need to know the specific characteristic of each strain. And as you might be aware that Indonesia is having so many islands and also sea water, so we have many also type strain of microalgae. So we have to select whichever having that ability to absorb high CO2, and also the biomass will give us a more value of product. Okay, next please. So here are the key takeaways: development for decarbonization, support from the government will be so much important, as currently the existing, we already got the research funding and grant from the Ministry of Education, and also we got the super tax deduction from Ministry of Finance. And future, there will be a carbon economic value to be implemented by Ministry of Environment and Forestry, and regulation of implementing CCUS is currently ongoing. And I think it's just been being announced that there will be a carbon tax being implemented in Indonesia. So the carbon tax will be subject to industry and private sector for them to give them a chance, either they pay a tax or they develop the technology to reduce the carbon. And collaboration and partnership opportunities on several area, like the green financing partnership, carbon trading program, technology improvement, and creating CCUS market and stakeholder acceptance. And to accelerate this decarbonization initiative and implementation, I think collaborative action may need to take into account. The more chain we develop, then the longer CO2 might be emitted to the atmosphere. I think this is all effort that we currently progressing. Hopefully it will inspire some of you, and hopefully soon it will come to the implementation into the commercial. Okay, next please. Okay, thank you very much for me. I give it floor back to Dian. Thank you very much, and sorry for the problem in the connection.
Thank you very much, Ms. Mersitarini, for your remarkable presentation. So we will have Q&A session in this, and Mrs. Shinchi will be a moderator to guide you for the question and answer.
Okay, thank you, Ms. Devi, for a very informative presentation. We have a few questions from the audience. There's a couple of questions on the use of methanol to blend with gasoline. One is, I think you referred to this a little bit already, but it's in blending of methanol to gasoline, the CO2 will re-enter the atmosphere and exits the carbon cycle. What's your view on this for helping the reduction of CO2 emissions? And also there's another question is about the car manufacturers' view on how much methanol they would like to accept to blend for their to maintain warranty. And can you share your views on these?
Okay, thank you. I'll try to answer the first one first. So basically, yes, as I present before that the utilizing the CO2 into other product may not really permanently reducing the carbon emitted to the atmosphere, but the way that when we have a methanol compared to the fossil fuel, it's already a way much lower the carbon dioxide that being produced if we compare among those two, the methanol and also the fossil fuel. So we always have to compare with what currently we have by now, and hopefully in the next future when the methanol together with the gasoline is being utilized in the gasoline, and then in the post combustion, and then it's going out, being emitted. And as I mentioned, hopefully in the next future, the natural sink might be enough, and also the direct air capture, the maturity technology may also be ready for that. And for the next question, what would be the percentage? Currently, we plan gradually, from 5%, 10%, and 15% of the additional alcohol into the gasoline. It's mixing ethanol, methanol into current gasoline, and hopefully it's already on testing and on negotiation into the manufacturer. Thank you, Kiko.
Okay, thank you. I would like to move on to the next question. This is related to the green methanol that you mentioned, I believe. For the use of solar energy, how do you manage the intermittent and the fluctuation of the solar energy used?
Currently, the solar energy is being managed by our subholding, Pertamina Power Indonesia. And currently, the reliability of solar PV must be followed with the battery, right? So the management of solar PV must be having also a battery that having a good quality of containment of the power. So how to manage the solar PV currently, it depends on the battery that we currently use. Thank you.
Okay, thank you. Now we have a few questions on the CCS projects that you mentioned in the first part of your presentation about the two projects, Gundi and Skowati. One is, how long did it take for the geological study in the East Java project to confirm storage capacity? And another question is, I understand these projects are ongoing for Gundi and Skowati under the JCM scheme. How did the Indonesia government select these fields for studies and implementation? What were the selection criteria?
Okay, thank you, Kiko-san. So basically, as we plan these two projects as the preliminary project for the CCUS in Indonesia, so we select the field which for the Gundi, and also specifically for the Gundi, that currently still in production actively of the gas. So it's a gas field, but there might be a declination in the next few years. So it's selected because when it comes to the declination stage after the peak, then the CO2 might start to enter. So there are a space in the subsurface formation to be filled in by the CO2, but we hope that it may cover in the next 10 years. And after several years, more than 7, we do hope that there might be an incremental gas production, because the CO2 that being injected into the lower layer will give a pressure to the upper layer of the gas there to be get into the top. So it's not directly a gas lifted way, like we call it EOR or EGR directly, but as we aim to store, but we might get still a benefit on the enhancement. And we plan there won't make any interruption in the production, because as you may also be aware that we have a target for the yearly production of the oil and gas for even the local domestic consumption. And we might still need to have some imported by now. So there we expect that there is no interruption in the production. Also same in the Sukawati area. Thank you, Kiko-san.
Thank you. I think we have one more question. In general, how much CO2 can be absorbed by utilization application, and how is it compared to the storage application?
For that, you mean for the Gundi?
I think it's a general question.
Okay, so it's a general.
Utilization.
Yeah, basically in our research, okay, yeah, if we compare to our research, it really depends on the we call it a molecular reaction, yeah. Like CO2 to methanol, if we're using the hydrogen, it can be 1 by 1. For the one ton methanol, you need 1 ton of CO2. But for if we take a look into the molecular for the biomass, it has a different calculation. And specifically for the CO2 injection, it's really depend on the capacity of field, and it's from one to the other. It has a different different and specific calculation. So we need to have a study first to calculate what would be the maximum capacity need to be injected, because it will depend on the characteristic of the reservoir, right? So the several study need to be taken first before we define and decided how many CO2 will be injected to that specific area. Thank you.
Okay, thank you very much. I think we've covered all questions now. Thank you. And now back to you, Ms. Dian.
Thank you very much for interesting discussion. For the interesting discussion and question for the participants. So next we will have presentation from Professor Yang, Dean, Chair, Associate Professor, Head of Green Catalyst Lab, National University of Singapore. He will present about research activities on CO2 utilization and potential industrial application. Please, Professor Yang, the floor is yours.
Thank you, Jem. Can you hear me clearly and see the share screen?
Yes, Professor Yang.
Thank you very much. First of all, I would like to thank the organizer for the kind invitation, in particular, Ms. Shinchi from MRI and her colleagues, as well as and the other organizers. I work in National University of Singapore, so I'm going to talk about CO2 conversion to fuels and chemicals. First, a very short self-introduction. I get my degrees in China at Peking University, and then I also spent 4 years in Switzerland before I joined National University of Singapore about 9 years ago in the chemical engineering department. My current research includes 3 directions. I'm the head of the Green Catalysis Lab. So what we do is related to sustainability as well as catalytic conversion. The very first direction is to create new pathways to make renewable chemicals. This is something we have been starting as long as I have established my independent research group. CO2 is one of the key feedstocks, a carbon feedstock. Apart from that, we also work extensively on organic renewable carbon sources, such as lignocellulosic biomass, as well as chitin. Then the second research direction is actually correlated with the first one. If we want to do these new transformations, we need to develop well-defined catalysts. These reagents are either inert, such as in the case of CO2, or highly functionalized, such as in the case of biomass. So the catalyst has to be very specific and tailor-made. Otherwise, we wouldn't be able to get these high-value products with high yield. This is something we're working on. And actually, we are also developing absorbent materials As I show in the example here, this is a recent result that we have developed a zeolite catalyst, a zeolite absorbent material that has exceptional high absorbent capacity towards CO2. The last research area is something we call dynamic catalysis. Maybe it's too technical, so I wouldn't go into too much, but the key motivation behind dynamic catalysis is to break the limitation intrinsically associated with the catalyst. So we would like to use commercial-based catalyst, but by doing this under dynamic condition to break the steady state operation, to enhance specific activity as well as product selectivity. So this is enough about myself and my research directions. Now I'm going into the major contents of today. I'm going to give you an overview of CO2 conversion to chemicals, and then we're going to be specific on two projects that have been going on at NUS for a number of years. One is CO2 to methanol, the other one is CO2 to formic acid, and I'm going to finish by introducing some of the ongoing research activities on CO2 conversion at National University of Singapore. If we look into history, actually, we are going to conclude CO2 utilization as a carbon feedstock is not a recent activity. Almost 150 years ago, we already started to use CO2 to make salicylic acid. And this is something already commercialized 150 years ago called the COPE process. And also not too far away from that, we are trying to make inorganic carbonates from CO2. Actually, it's not really from CO2 gas, it's from calcium carbonate. By decomposing that, we get CO2, and then we use this CO2 to generate sodium carbonate. This is the Solvay process that is even used today. Then about 100 years ago, we start to use CO2 to react with ammonia to make urea. This is here the largest utilization process of CO2 to generate fertilizer. Okay, and this is soon commercialized after the Haber-Bosch process being commercialized. It's not recent, and actually over the past 1 century and 1.5 centuries, many routes becomes possible. So the chemicals in the box on the left-hand side represents industrial routes. Either they are practiced in full scale, in commercial scale, or at least they are demonstrated under pilot scale. It's a range of products from aromatics, from fertilizer, from methanol, from carbonate to polymer. All these are already demonstrated in the relatively large scale. And then on top of that, if you look into literature, many more chemicals are available from CO2, but these are not commercialized yet. So what is the problem? CO2 conversion to chemical is not a new research topic, but now it becomes more relevant when we start to talk about the role of CO2 capture and utilization in the mitigation of climate change. Before that, CO2 is purely regarded as a carbon feedstock, as a C1 convenient carbon feedstock. Sometimes we want to make some oxygen-containing chemicals, in particular, the ester type or carboxylate type compounds. It is convenient to utilize the existing CO double bond in CO2. But now we get, the topic becomes hot again when we try to understand whether CO2 utilization can make significant contribution to the mitigation of climate change. First, I'm going to share something that is very negative on this. It's a paper published 4 years ago in Nature Climate Change. If you read the abstract, it says it is highly improbable the chemical conversion of CO2 will account for more than 1% of the mitigation challenge. And the main argument in the paper is that there is a scale mismatch at present, which is true. If we look at the current utilization of CO2 in making chemicals, even the most abundant one, as I mentioned just now, is urea. It's 180 million ton scale. The methanol is 3 times lower. And then even for inorganic carbonates, it's on a similar scale. compared to Europe. So based on the current situation, CO2 conversion to chemicals would not contribute significantly to climate change, to the mitigation of carbon. Okay, then how about the future? If we look at the full potential of CO2 mitigation potential, we have to look at the scale. For the transportation fuels, it is produced at 5 gigaton, more than 5 gigaton per year. Then for the bulk chemicals such as ethylene, propylene, and BTX, all these bulk important chemicals combined is in the range of 1 to 5 gigaton per year. And then for polymers, fine chemicals, for these more specific specialty chemicals, they are typically in the range of 0 to 1 gigaton per year. If we come back here, if we look at the scale anticipation, the scale bar is gigaton scale. And therefore, if we are talking about mitigation plan, then we really have to consider making fuels or at least bulk chemicals from CO2. There is an excellent question from the audience just now asking if we make CO2 into fuels, okay, rather than such as methanol, and then we burn methanol, CO2 goes back to the atmosphere. So it doesn't really mitigate CO2. This is right and wrong at the same time. If we only consider, yes, CO2 goes to methanol, let's say the process relies on renewable energy, the process doesn't create extra CO2, and then we burn methanol to get the energy out of it. So the net effect is we don't remove any CO2. However, this is a process that should be compared with the current fuel production and consumption based on fossil fuels. Okay, now we actually dig these fossil carbon underground and we burn them, they become CO2. So we are actually converting organic carbon into CO2, which is completely different here if we are able to convert CO2 into fuel and then burn fuel back to CO2. If we compare that with the same energy generation, we are going to achieve 0 CO2 emission if the process relies on renewable energies. Okay, so that is my view for CO2 to chemical. In the longer term, it does has a role to play. In the longer term, we shouldn't, CO2 alone, conversion of CO2 alone to chemicals wouldn't solve the problem because CO2 has so energy level. We always need energy input. But then CO2 should be regarded as a renewable carbon feedstock. If we want anything, any transportation fuel still based on carbon, or if we want any chemical that is carbon-based, and in the longer term, we don't want to rely on fossil fuel anymore for our carbon source, then CO2 is one of the few sources that are available, cheap, and abundant. Of course, apart from CO2, we can also imagine biomass as an organic form of carbon source to make carbon-based fuels as well as carbon-based chemicals. But then biomass actually also comes from CO2 by photosynthesis. Okay, so at National University of Singapore, we are considering the chemical engineering in the longer term, in the very far future. In the far future, when we don't rely on fossil fuels anymore, all the CO2 problems come from the use of fossil resources. So the ultimate goal should be get rid of them and rely as much as renewable energy as possible. Under that long-term vision, we are trying to consider from a system approach to lead our research innovation. So we are thinking if we still want carbon as a transportation fuel source and chemical, this is under debate. Within National University of Singapore, we are also working on, for instance, nitrogen-based energy carrier, such as ammonia. In this case, we completely get rid of carbon dioxide. We completely rely on carbon-free fuels. So that's a parallel research direction that is a competing technology. However, we should still be optimistic about CO2 to chemical because if we want to use carbon-based chemicals, all these organic chemicals are carbon-based. I can't imagine we can find replacement chemicals based on non-carbon material. This is almost beyond my imagination. So if we talk about all these bulky chemicals, they have to come from carbon, then CO2 or biomass should have a role to play. If we come back here, then the carbon source should be CO2, Then we are looking about renewable electricity, which can give us hydrogen. Then combining these two will be able to lead to the formation of platform chemicals, such as alcohol. It can be other chemicals as well. And then from methanol, in our last speaker, excellent presentation, it has already been pointed out, alcohol is an excellent platform that can essentially lead to all these. Many have already been commercialized. So once we have this alcohol, we don't even have to directly blend methanol to gasoline. Methanol is problematic when it is directly used as a fuel because it might contain water, it has low energy input, it doesn't tolerant with the current engine when the percentage is too high. So there are potential problems, but upgrading of, for instance, methanol to other high value chemicals are at least at the pilot scale. The feasibility have already been proven. On the other hand side, we are also looking directly to upgrade CO2 by electrons generated by renewable energy into chemicals. Again, these two are competing roads. Here, the generation of hydrogen is rather mature, so we need to develop highly effective catalyst that is able to convert hydrogen and CO2 into the platform chemicals. And on the right-hand side, it's a higher challenge scientifically. We want to use the electrons directly to upgrade CO2 into a higher energy form. Okay, this slide actually shows the entire team working on CO2 project, what is called Green Energy Program within NUS. 3 years ago, National University has launched this program and internally funded 80 million Singapore dollars, that is about $6 million US, to support to kickstart such a research tackling CO2 conversion to chemicals. Actually, more than 5 departments are involved and 15 faculty members are working jointly on the project. So far, altogether, we have about 40 within the team to tackle the problem. And because of this diversity of the team, we have expertise from molecular level design of the catalyst all the way to reactor design, as well as system engineering. Of course, we don't really build the large reactors and plants inside the campus. That's impossible, but we do have the capability to do the designing, at least in the computer, using software on the reactors and plants. Also, the university provides sufficient support to build the research infrastructure. These are some of the equipment that are built under the support of the program that includes the fully automated synthetic robot, which is able to produce 32 catalysts at a time. In contrast, a student or a research scientist a day can make 2 to 3 catalysts, experienced one, but this guy is 10 times more effective. And to cope with the synthetic capability, we also built a multiple channel reactor that can evaluate 4 to 8 catalysts per time. And also at the scientific level, to really understand how these catalysts work to convert CO2 into chemicals, we have built in situ and TEM facilities. And then in the larger scale, we purchase extruder. When the catalyst is promising, we have the capability of making catalysts at larger scale. Now, that's probably enough to provide an overview of CO2 to chemical, as well as the research infrastructure and facility and team in the National University of Singapore. Coming up, I will be spending the next 10-15 minutes talking about CO2 conversion to methanol and formic acid. First of all, why methanol? I have to be honest, the first reason of methanol is easy, comparatively easy to make. It is a C1 chemical. Basically, what we have to do is to remove 1 oxygen from the carbon dioxide and add 4 hydrogen to the molecule, 3 to carbon and 1 to oxygen. And by doing that, we will be able to get methanol. There has already been a lot of research there, and pilot scale plants are built in the world. So methanol is relatively a lower hanging fruit. Okay, so it's relatively easy to make. And also it's not only because of that, and also methanol has a lot of advantages. If here we compare the energy density of liquid, basically in general organic liquid, to many other formats of energy carriers, such as hydrogen gas or hydrogen gas under pressure or under liquid form, or the natural gas or the batteries. In all these comparisons, organic liquid will compare favorably, even if methanol is not as good as ethanol or conventional gasoline or diesel. But if you put this into the context of the all possible means for the carriers, then methanol is quite exceptional. We can have even more obvious observation based on the figures here. This is the energy consumption projected in 2015 for 3 hours for the entire world. So by that time, the entire globe would consume 94 TW of energy in 3 hours in another 30 years. So here is an assumption of how much energy is needed, how much energy carrier is needed based on one football ground. In the bottom is one football ground. If we use methanol, the height will be 3 kilometers. If we use compressed hydrogen at 200 bar, it will be 42 kilometers. With the lithium-ion battery, it will be 26 kilometers. So again, methanol is such a dense energy carrier, so that it carries orders of magnitude higher energy density compared to some other means. On the right-hand side is the weight. So how much weight does this transfer to? It transfers to, for a methanol, it transfers to 60 Airbus A380. For hydrogen, compressed hydrogen, it's 350. For lithium-ion battery, it will be 1,700. So again, it's orders of magnitude difference in terms of weight. And on the left-hand side is in terms of volume. So methanol compares favorably to many other carriers of hydrogen or energy. In fact, it's not only weight and volume, methanol also compares favorably in terms of economics. If in the future, we believe in hydrogen economy. If you don't believe in at all, that's another story. If we have some faith in the hydrogen economy, then for the cross-continental transportation of hydrogen energy, we have to consider a carrier. There has been study, if you cross-continental, basically you can't use pipelines. You have to either consider transport hydrogen directly in the physical form, in the liquefied form, or in the high pressure form. Or we have to transport hydrogen in the organic carrier or any carrier form. There has been studies saying that the carrier will be much more affordable than directly transfer hydrogen as a gas, in the physical form, either high pressure gas or liquefied form. And if we do a more detailed calculation, this is from a recent literature, actually methanol is one of the most economically viable solution as a hydrogen carrier. The total cost means including the hydrogen production cost, including methanol formation cost, including transportation cost, and also including eventually the releasing cost of hydrogen a few years ago is about 12 euro per kilogram. And then only ammonia is comparable. Ammonia is providing a similar cost as a carrier. Then this one is has been heavily studied by, and even in under commercial use to some extent, in particular by a few Japanese companies, at least based on this study, it's around 10 to 20% more expensive. Okay, if we further break down, $12 per kilogram is still a big amount. It's still very expensive. So that raises a question mark. Even if methanol is comparatively economically competitive, would it eventually stand a chance to compete with the other routes? So we have to really look into how does that 12 euro comes from. Actually, a majority comes from the hydrogen production cost at present. We are not talking about hydrogen from natural gas. We're not talking about hydrogen from coal. We are really talking about green hydrogen based on the current technology using renewable electricity to do water electrolysis. So that's the cost for hydrogen production, but many researchers are expecting this cost to drop by 70–80% in 10 years. So we can expect a dramatic drop of hydrogen cost. If we look at the other two major cost drivers for methanol as an energy carrier, one is the cost of CO2. The other one is the production cost, because the production of methanol needs energy. So it's energy consumption and operational cost during the synthesis. So the CO2 capture cost would also be expected to drop over the years. And if this the feedstock cost can really drop, then the driving force, the decisive factor might be the operational cost. There is still plenty of room for us to decrease the operational cost of methanol formation from hydrogen and CO2. The science and technology gap that we identified for the operational cost is that the existing heterogeneous catalysts are insufficient to conduct CO2 to methanol. This is drastically different from the commercial methanol synthesis from syngas. Syngas to methanol has been commercialized. The current catalyst is copper zinc oxide. That's still the most popular catalyst for converting CO2 to methanol. But even if syngas to methanol has been commercialized as early as 1960s, it has been used over 50 years. The zinc copper catalyst may not be the best catalyst for CO2 conversion to methanol because the stability issues. CO2 conversion to methanol is going to generate more water, and under higher moisture condition, the stability based on some study of the copper-based catalyst will be compromised. So our attention start to be given to another emerging category of catalyst, zinc zirconia. We call this our first generation catalyst. Dr. Han Phoumin is a major person work particularly on this project, and our key collaborators, including Javier from ETH and also Sergey as well as Chen from National University of Singapore. Let me tell you a little bit background of this catalyst. As I mentioned, the dominant catalyst now used is copper zinc oxide. And then zinc zirconia oxide is a relatively new catalyst for methanol synthesis from CO2 that is first reported 4 years ago by Professor Li in Dalian Institute of Chemical Physics. And actually a few years later, a pilot scale demonstration was built in Nanzhou, China, based on zinc zirconia oxide catalyst. The catalyst has advantages and disadvantages at the same time. The advantages, it is very stable. In 600 hours, there's no deactivation at all. And also the selectivity towards methanol is high, but the downside is compared to the more popular copper zinc catalyst, it's less active. So when we entered this field 3 years ago, at that time, the zinc oxide is first being introduced to the community. We believe there are huge rooms for further improvement of this catalyst. So our very first study is to enhance the activity of the zinc zirconia catalyst. And we actually studied the catalyst in detail, and we recognize why CO2 conversion to methanol is slow is because zinc and zirconia do not activate hydrogen well enough. Hydrogen gas cannot be easily activated. Activation of hydrogen is redetermined over this catalyst. So to solve that problem, if you work in catalysis, then immediately comes into the mind is to add some palladium, because palladium can even activate hydrogen at room temperature. So what we did is to add up to 1% is not allowed. We don't want to increase the cost of the catalyst too much, up to 1% of the PD into the zinc zirconia, and we want to disperse the PD as uniform as possible so that every site of zinc and zirconia can benefit from the activated hydrogen from PD spill over to other sites of the catalyst. So to achieve that, we have engineered the catalyst so that the PD atomically disperse. The dark color, this dark green or blue color represents PD. We really allow PD to atomically disperse in the entire matrix of zinc zirconia. And we actually have evidence for that. We don't see any palladium nanoparticle, but instead we see atomically dispersed or single atom PD dispersed in the matrix of zinc zirconia. With this catalyst, actually, we run the methanol synthesis reaction. First, as expected, it's about 50% higher in producing methanol compared to what has already been practiced in the pilot scale. This is the 0.4 gram of methanol formation per gram of catalyst per hour. But this the new catalyst provides 6 gram, 0.6 gram of methanol per gram of catalyst per hour. But it's not the end of the story. It's actually eventually the results is even higher than our expectation. As I mentioned, a benefit of this zinc zirconia catalyst is very stable. And indeed, we are able to reproduce it. We did 100 hours for now. There's no sign of any deactivation. But after adding PD, actually the catalyst gets further activated. So from the initial activity of 0.6 increased to 0.7 grams per gram of catalyst per hour. This is more than 10%, it's about 15% enhancement. And the trend does not seem to stop there. We need further analysis to see eventually how this can go. So it's already good, but actually we didn't stop there. As a fundamental researcher, my research fellow has continued along the way. We developed the second generation of catalyst. In the first generation, there's a downside I didn't mention, that the formation of methanol has enhanced significantly, but the direct contact of PD with zinc zirconia also induced the formation of CO that is not entirely wanted in methanol synthesis. We still want to increase the methanol selectivity without forming too many other products. So the second generation of catalyst, we still rely on PD, but now we separate PD away from zinc zirconia. So PD is still able to help us to activate hydrogen, but at the same time, PD cannot activate the CO2 species absorbed on zinc zirconia to form CO, which is unwanted. We tested this idea using a bunch of PD catalysts together with our zinc zirconia, and we actually found a really good recipe under one specific condition. This is the pure zinc zirconia, and this is the addition of 2 active components. So zinc zirconia plays a role to make sure CO2 converts to methanol, and the PD as the second component makes sure hydrogen gets easily activated. And under this particular condition, it's 7 times higher, more active than the benchmark zinc zirconia catalyst. We actually tested in the entire regime on the right-hand side. If we do at lower temperature, it can be even 10 times more active, even under optimum condition. And it is 2 times more active than the zinc zirconia catalyst, which I showed here. It's about 0.4 grams of methanol per gram of catalyst. This one is close to 0.8 grams per methanol, or gram methanol per gram of catalyst. We also made a lot of fundamental study. How intimate should these 2 components be? But I think that's a bit too technical, so we can escape that. And our understanding of the promotional effect is now we have 2 catalysts doing 2 jobs separately. The PD is in charge of hydrogen activation and then transfer to zinc zirconia, so that the activated hydrogen helps CO2 hydrogenation into methanol on the second component. All right, now this is a brief summary of the methanol project. CO2 to methanol, we launched it 3 years ago. And then last year, the entire team has formed. I show you the team, and all the facilities are in place. And we started to do basic science research. And this year, we actually have secured external funding support, another few $1 million. I'm going to mention a few continuation projects at the last stage. We managed that. Actually, there are 3 projects funded by National Science Foundation with the overall supporting level of more than $10 million. And we also established strong collaboration with local industry. So now we are able to conduct the R&D effort in full capacity. In a few more years, when government invests over 10 million, certainly they don't only want academic breakthrough, they're really expecting we create IP for new generation of catalysts, we create IP for new system level design that is most suitable for the new catalyst. And in a few years, we are expected to be able to demonstrate in pilot scale. And then by 2028 or near 2030, we hope one of these approaches could be adopted at full scale. Now, I will spend a bit less time on the formic acid project. Actually, formic acid, we have less expectation because formic acid has a lower energy density and also has a lower hydrogen storage capacity. On the other hand, formic acid has its own advantage in the sense that it's very easy to make. So the production process has minimum consumption of energy. This is one of the easiest products that can be formed from CO2. So, and it's reversible. We can relatively easily generate formate, and it's also possible to generate, release the hydrogen from formic acid by pretty much by the same catalyst. We spent a few years looking at the effect of support, looking at the major component. Again, we like plating. Plating can both activate hydrogen, can also conduct CO2 to formic acid. We actually spent a few years to understand which plating is good and which support is good. And based on this fundamental study, we proposed a catalyst designing principle in general for CO2 hydrogenation by encapsulation strategy. Pretty much we are always using a second component to modify PD, so they deliver the highest activity, and at the same time, we encapsulate this species, this active species within the pores of the support. So they are very stable. This has been actually receiving some recognitions in the community. The bimetallic encagement is recognized as a widely applicable approach to conduct CO2 hydrogenation. I'm going to show only one example along this line. We made a zeolite catalyst. This is a pure silica zeolite. In order to encapsulate the active sites within the pores, we have to make the synthesis from the beginning by including the metal precursors. So plating and magnesium is added from the beginning. Along the way of zeolite formation, they are encapsulated, these precursors are encapsulated within the pores of zeolite, and then finally by calcination reduction, they are firmly conformed or fixed inside pores. That makes them, the size is small, so they are active, but at the same time, because they are covered by zeolite pores and it's a hard template, they cannot decompose, they cannot agglomerate, or it's not easy for them to leach. Based on this catalyst, we actually achieved currently the best record for heterogeneous catalyst for formate formation as well as formic acid decomposition. We also conducted a system level design, and we built a really small one in the lab to demonstrate actually ultra pure hydrogen is produced. It has the carbon monoxide is less than 5 ppm generated in this process, and this hydrogen is pure enough to directly promote the PION fuel cell. We have a demonstration on that. Okay, and finally, I will use the last few minutes to introduce a few ongoing projects. In the first phase of the green energy program, we focus on some, as I said, lower hanging fruit, methanol formic acid. In the next stage, we are targeting something that are a lot more challenging. Overall, I'm going to share 3 research projects. The first one is led by my colleague, Professor Zhen Huachun. He is looking into making CO2 into higher alcohols. Okay, in methanol, it's relatively easy, as I mentioned. The key chemistry there is to activate hydrogen, so hydrogen can be added to carbon, hydrogen can be used to take the oxygen away from CO2. It's relatively straightforward and simple, but now if we are targeting higher alcohols are better than methanol in a sense that they have higher value in the market, they have higher energy density, and they are more compatible with the fuels. And for instance, ethanol has already broad application to directly blend with the gasoline. but scientifically, it's a lot more challenging. The key step will be to engineer catalysts that can conduct the CC coupling step on the surface. And this is not a trivial task. We do have some catalyst design principles. One specific example Prof Chen is looking at is the copper zinc bimetallic clusters that, based on our DFT calculation, will favor the surface CC coupling to form C2 products. Now his team is working very hard to prove the concept. The second research project at National University of Singapore under Green Energy Program is to use electrochemical conversion pathway to directly convert CO2 to chemical. As I mentioned, this is a competing road. It's a competing road to the thermal pathway. In the thermal pathway, we also rely on renewable electricity, but we rely on relatively mature water electrolysis. We get hydrogen. So it's a thermal conversion using the energy in the hydrogen to upgrade CO2 to fuel and chemicals. But here it's philosophically a more direct and better approach because it's a single step to convert CO2 into fuels by using the energy, electrical energy, electricity or electrons. But certainly it's difficult. There are many competing roads. Water can be reduced as well, for instance, and for CO2 reduction, there are multiple chemicals available. You can get CO, you can get methanol, you can also get even more high value added chemicals like C2 chemicals. So the focus of the team is to develop novel system with record to achieve record high energy efficiency and a single pass conversion. So they actually have done some economic analysis if the technical target can be met. Of course, we don't know now, but if such a target can be met, it will be economically competitive with currently existing roads. Let me skip there. Then the last project I would like to share is CO2 to food. This is a new project that we are very excited about. And also it has a special, we do believe it has a general implication to every place, but also has a special importance for small cities such as Singapore. Let me first introduce what is the key concept behind. If we think now, how do we produce food? There are actually two steps. The first step is plant cultivation. We grow plant in the land. Then the crops normally takes a few months to grow. This process, what is the nature of this process is we use renewable energy, that is solar energy, to convert CO2 into organics. The building block is glucose. That's how nature selected. Nature selects glucose as the building block, CO2 with photo energy, with water to glucose. And then from glucose, we build up cellulose, lignin, or whatever components in these plants. Then in the second stage, when we want protein-enriched food, what we do is to use these plants to feed the animals, in particular cows, sheep, chicken, pigs. So these animals actually eat these plant-based biomass and they get enriched in protein and lipids. So this is the current model of the food production. And this process, in particular, the animal feeding is heavily associated with CO2 emission. There are estimations that every 1 kilogram of beef, we generate 40 to 50 kilograms of CO2. So actually the entire idea was inspired by what we are doing currently. So in the future, we want to do it in a chemical engineering and bioengineering manner, a combined chemo bioengineering manner. Okay, we actually have a term for this, green chemical farming. In the first step, we want to do it in a chemical manner. We don't want the plants. We are not so patient. Plants takes months to grow. But actually, if we do CO2 directly with hydrogenation reaction, the capability, the productivity per unit square of land is 1,000 times higher. In 1,000 times higher productivity, we will be able to end up with some organics. It's difficult to make glucose, but it's not so difficult to make ethanol and acetate or formate. We are already able to do that. Then in the next step, my other two colleagues, Prof Tong and Prof To, are going to utilize these organics, these organic chemicals the same way as currently the living organisms use glucose. Okay, so these are the new building blocks directly from CO2. We are going to use them to feed the algae and engineered yeast. So they are able to produce multiple component useful products, proteins, lipids, even vitamins for us. Then, of course, in the downstream, we have to figure out the safety issues. We have to figure out the downstream production issues. So eventually, they become the food. Okay, as I said, we call this green chemical farming concept. It's in general applicable as a way to make food in a more compact, energy less intensive, resource less intensive manner, but also it's particularly applicable, for instance, in the regions with land constraints, with regions with little fresh water supply, because we don't really need fresh water anymore along the process. Algae can grow in seawater, hydrogen can come from seawater as well, and as well as hostile environment in outside the Earth, if we still dream to go to Mars, for instance. With that, I would like to conclude my presentation, and I would be happy to address any question you may have.
Thank you very much, Professor Yang, for your comprehensive presentation. Now we are getting to the Q&A session. Will be led by Ms. Shinchi. I pass to Ms. Shinchi, please. Thank you.
Thank you, Ms. Dian, and thank you, Professor Ning Yang, for a very thorough and informative presentation. We have a few questions from the participants. First one, I think this is the similar questions already asked to Ms. Devi as well, but what is the ratio of CCU contribution compared to CCS and EOR? What is your estimation or target? I think this,
yes, at present, it's at present current production scale, it's the minimum. I actually agree with the Nature Climate Change article that if we don't change the model for now, the CCU contribution to CO2 mitigation will be around 1%. The situation might change if we are more ambitious. If we are not happy, we are not just happy, you know, we burn fossil fuels, let's then bury them underground. So if we are more ambitious than that, if we are really thinking of based on renewable energy future, then CCU will have a bigger role to play. If we really develop hydrogen-based economy, then this approach, even if, again, even if the fuels are eventually after burn goes back as CO2, but we have to consider what's the source for this fuel. If the fuel in the beginning is CO2, it doesn't induce any net emission at all. In that scenario, if we only look at the scale, it can contribute 5 to 10 gigaton scale. If you talk about that scale, it's 20% of the current emission. So that's probably the higher limit. That's a dream. I don't think it will ever achieve that, but it's probably give us a range of the capability. It will be somewhere between 1% to 20%.
Okay, thank you. And I think this partially answers another question. Another question was, it's more of a comment, I think. A standard CO2 storage project is able to permanently store in safe and suitable storage site for at least 1 million tons per year. And this is, I realize this is not an either or contest, but I'm curious to know how this compares with the utilization opportunities you have explained. I think I partially already answered to this question, but if you want to add something, please.
Yes. I think they are not really competing. Again, if we are talking about we are burning fossil fuels, then you have to bury them underground because you take them from underground, eventually you put them back to underground. If we are thinking about using renewable energy, then we get certain carbon CO2 source. We make them into fuel, we burn them. You don't have to consider because CO2 is from atmosphere or some waste gas anyway. Yeah, they are not really competing.
Okay, thank you very much. And now I have another more technical question. For CO2 to methanol solution that you mentioned using palladium as active site. And palladium is known to be expensive and rare. Have you ever tried replacing palladium with other common metals? So the overall process is more economical on larger scale.
Yes, this is an excellent question. We actually tried other methods. We were at a lab scale, we actually tried all the possible methods. But what I can say is copper is good. Copper is actually is better than we don't dope anything. Not as good as PD, but copper actually can work. Eventually, which one should be used should be on a thorough economical analysis. Based on our current estimation, based on the stability of the catalyst price is not a driving issue. The price of a catalyst contributes to less than 10%, only a few percent of the entire process. The cost driver is the energy input inside the process. So if the catalyst is able to increase the unit time productivity, decrease temperature and pressure, it will actually save the process more. So far, I don't have the exact number, but that's our impression. Of course, sustainability is a problem. If we are thinking about really gigaton scale production, then we may not have enough PD as a catalyst. In that case, it's not an economic problem, but more of a sustainability problem. Then copper might be our alternative.
Thank you very much. Now we are receiving more questions. I'd like to move on to the next one. Have any of the trials that you mentioned looked at the presence of contaminants in the CO2 in case where it is applied directly to flue gas, or is CO2 separation still required?
We didn't yet. That's actually of course, a good question. We didn't look into the contaminants yet. We are assuming this has to be combined with the CO2 capture technology in the power plant. So we actually have pure CO2. We do believe this with this additional step, it's actually better. Otherwise, we are going to compress very diluted CO2 from flue gas in Singapore. It's only 5%. But the CO2 hydrogenation is always under high pressure, which means if you need 10 bar of hydrogen, you need to compress the flue gas into 200 bar. This will be simply too costly. So actually, it's even add one more step, it will be economically more viable.
Thank you very much. And now there's another question. It's about also it's about impurities as well, but in relation to the green hydrogen generated. Are there any traces of CO2 or moisture that are normally detrimental to catalysts in the green hydrogen?
Very good point. We, at least for our catalyst, we don't see any detrimental effect of water. Actually, water is generated in CO2 hydrogenation. We see CO2 lose one oxygen, that oxygen becomes water. So water is always there, regardless whether it's present in the beginning or generated in situ. Our catalyst, one advantage is our catalyst is very hydrostable. For oxygen, we didn't test that. We are using pure hydrogen and the CO2. So for now, we don't know entirely what is the effect, but I suppose if it's only trace amount, I'm not too worried because hydrogen is in excess, and in the presence of trace amount of PD, for instance, this oxygen goes to water very quickly. Then it becomes the same issue as water.
Thank you. Now I would like to address a more broad question, possibly on the hydrogen economy that you mentioned. The question asks, in the utilizing of CO2, there is assumed to require investment in hydrogen and energy, including renewable energy. As of now, how do we address these factors, especially in particular to Singapore?
Very good. Gary, it's an excellent question. Singapore position itself as always as energy importer. That's the situation for now. We import crude oil, we import natural gas from Middle East, from Malaysia, from these neighboring countries. We generate energy. In the future, if the entire world transform into a more renewable, more sustainable form, we are still going to import hydrogen-based carriers. This has been well positioned. Singapore cannot generate enough hydrogen by itself. But however, on the other hand, we are trying to do our share in Singapore in fundamental research. So NUS, now we already, you see in the first stage, we're already working on CO2 conversion. In the next stage, in next January, National University of Singapore will announce the establishment of Hydrogen Center. So we are looking into hydrogen production, hydrogen transport, and hydrogen utilization as the entire supply chain. Of course, of particular relevance to Singapore is how do we transport hydrogen here, and how do we release the hydrogen and best utilize the hydrogen or other forms of carrier. But the research-wise, well, there's no limit. We are doing all sorts of research.
Thank you. Now I'd like to take one last question. I think this brings us back to the general question that we asked Professor Yang to answer in the beginning. To generate methanol with CO2 and green hydrogen does not seem to match the decarbonization scenario. What do you think of it? Perhaps you can again share your views on this.
There seems to be a lot of concern on this one. Let's say even if we have power plant, you generate CO2, you 1 million ton, you bury underground permanently. Let's say you can do it permanently. Okay, you reduce 1 million ton CO2 emission, no problem. In another scenario, let's say 1 million ton of CO2 is converted into methanol using renewable energy, and then we burn that. We return that 1 million ton into atmosphere. It seems we didn't really do any decarbonization, but it's wrong because we actually produce 1 million ton of methanol. We are going to reduce the consumption of 500,000 ton of petroleum. And that 500,000 ton of petroleum is going to emit also at a million ton scale of CO2. We avoid that. So even if we use the power plant derived CO2 to make methanol and then burn it, we are reducing CO2. Not as good as permanently putting them underground, but we also make use of it. We generate new batches of fuels. Yeah.
Thank you for clarifying, making clarifications again. Actually, I said one last questions, but actually, if you can bear with me for one more. From the organizing side, we want to ask about the cost competitiveness of the CO2-based chemical products that the NUS is developing.
So far we have a relatively mature technology for methanol and the formic acid. If we compare these two, I would say methanol is better. Methanol is better, but in the longer term, we don't have numbers for the others. But actually, the reason we do some others is that some other chemicals in the short term will be more economically viable. In particular, C2 and C3 products. Like propanol. Propanol is one of the targets. Propanol has a much higher market price than methanol. So, but again, if we are really talking about CO2 mitigation, methanol is the most promising one. If you look at the scale of propanol, it's the orders of magnitude lower. So it's about economic viability or mitigation capability. So they don't always match with each other.
Well, thank you very much for answering all of the questions. And now we have come to time to conclude the session. I will give the mic back to Ms. Dian one last time.
Thank you, Ms. Shinchi.
Thank you.
Thank you, Professor Yang. Thank you, Ms. Shinchi, for leading the question and answer and discussion in this session. Before we end today's workshop, I will let Ms. Shinchi to say a few words for her closing remarks. Please, Ms. Shinchi, the floor is yours.
Okay, thank you, Ms. Dian. Again, this is the last day of our technical workshop series, and we were very honored to welcome two experts on the CCUS utilization activities. And Ms. Dewi Mersitarini from Pertamina Indonesia kindly informed us of all the activities that Pertamina is engaged in, and all the possible industrial applications. We were able to see the big potential in the technologies that you mentioned. And Dr. Ning Yang, I think Dr. Yang gave us the big picture, but also the very focused picture as well. And I think it was very informative for all the participants to know where the CCU stands in the big decarbonization picture. And I think from the Q&A session, we were able to clarify that CCS and CCU are not in competition with each other, but we need both if we really want to move towards the decarbonization society. And I think Dr. Yan also mentioned a lot of other possibilities in industrial application, and including the food section that you mentioned in the very last part. It was very interesting. So big applause to the two speakers today. Thank you again. And what I would like to share one last remaining information from the organizer side. The Mitsubishi Research Institute, commissioned by ERIA, is now conducting a study to look at the technologies available, investment required, and a legal and policy framework desired to make a successful project case in the ASEAN region. And we will take into account all the valuable information gained through the lectures, technical workshop sessions as well. And the outcome of our study will be shared in the workshop, again, in a similar format to this, in online workshop at some time in the first half of December. So if you can keep an look out for the ERIA website for any updated information, I would be very much grateful. And I look forward to seeing you all again in future ERIA workshop. Thank you.
Thank you, Ms. Shinchi, for your closing remark. So we come to the end of today's workshop and the whole CCUS technical workshop series. Thank you to all speakers and participants for your insights and fruitful engagement in this 3-day CCUS technical workshop. For your information, we will have the 3rd CCUS Knowledge Sharing Conference. Sorry, let me share my screen for the announcement. So we will have a 3rd Asia CCUS Networks Knowledge Sharing Conference will be held on 14 October, upcoming 14 October. We will have OGCI, Oil and Gas Climate Initiative, and then Petronas and JOGMEC Japan will be our speakers and commentator. So if you like to participate in that event, please see our website in www.asiaccusnetwork/area.org to register the event. So thank you again for all, and with that, I will conclude this workshop. Thank you.
Thank you very much.